Okay, so we're going to begin going over our final exam review question by question so that you get, some help and hopefully this will help answer some of your questions if you're struggling to arrive to some of the answers. So for your first one, how do you calculate molar mass of a compound? Well, it's the sum of each atom in the compound, okay? Sum of each atom in the compound. Okay, so if we look down to question 2, it kind of makes a little bit more sense as we work them out. So I have the compound MgCl2. Okay, what I'm going to do is I'm going to break that up into each atom, so Mg and Cl. Okay, and I'm going to find the mass of each of those. So I'm going to have to look at my periodic table. So Mg is 24.3. Okay, and Cl is 35.5. I'm just going to kind of round those to 1 decimal for right now. So 35.5. But again, we're talking about each atom. Because I have 2 Cl, okay, it means I have 2 atoms of chlorine. So I'm going to multiply those, okay, and I'm going to get 71 here, 24.3, all right, and then I'm just going to add those together, which gives me 95.3. Okay, so for your molar mass of MgCl2, it's 95.3, and then molar mass is in grams. Okay, so I'm essentially doing that for every single question here. Okay, so I'm just going to break up each element. Okay, so I've got carbon, hydrogen, oxygen, and another hydrogen over here. So when I account for the molar mass, I need to account for how many atoms are in each of those. So with carbon, I'm going to have to multiply whatever number it is by 2. With hydrogen, I have 5 here and 1 here, so I'm going to have to multiply by 6. And then I have 1 oxygen there, so I don't really have to write 1, but I've got 1 oxygen there, and I'm going to find the mass of each of those. So with carbon, 12.011, okay. With hydrogen, if I'm looking at the periodic table, it's 1.008, and with oxygen, it's 15.999. Okay, again, I can kind of use a rounded version of that if I want to. My periodic table is a little bit specific. So then I have each part. I'm going to add them all together. It's going to give me 46.069 grams. Okay, for B. All right, so this is A, this is B. And for C, some of you kind of get confused with these parentheses here. Just remember that whatever subscript is attached to the outside of the parentheses, okay, so if you see here, I've got the 2. All right, this 2 is going to distribute to everything inside of there. All right, so here I've got 2 N's. All right, so I'm going to go ahead and just kind of like write out all my compounds. So I've got N, H, S, and O. All right, so I've got 2 N's. Okay, I've got 4 H's on the inside, but because I've also got another 2 on the on the outside of us, or as far as this subscript, I'm going to multiply those. So I've actually got 8 hydrogens. Now, this compound SO4 is on the outside of the parentheses, so nothing distributes to it. So S is by itself, so there's just one of them. And then the 4 is only attached to the oxygen, so 4 times. All right, so I'm going to kind of save myself a little time. You just need to find the mass of all of these substances on the periodic table, multiply them by how many you have, then add them all together. Okay, so when I add them all together, I've got 132.14 grams. Okay, so that's how I'd find the molar mass of each of those compounds. For number 3, what is needed to convert moles of a substance to mass and atoms to moles? Okay, so for the first part here, so moles of a substance to mass. Well, if I'm going to convert moles to mass, I'm going to need molar mass of the compound. Okay, and that would go back to all these steps that we just did right here as far as finding the molar mass. Okay, so we've got to do that process if we're going to convert moles to mass. If we're going to convert moles to atoms, or with atoms we could say molecules or particles. Okay, molecules, particles, atoms, they're all kind of talking about the same thing. We're going to use Avogadro's number. Okay, you need Avogadro's number, which is that kind of magic number there, 6.02 times 10 to the 23rd power. Okay, so you're going to need that in order to solve for moles to atoms. You need molar mass to solve from moles to mass. Okay, so let's look at some conversions here. So how many moles are in 5.3 times 10 to the 13th atoms of water? Okay, so again, here, these are numbers. It's written in scientific notation, but it's just a number. Okay, I can plug that in or just start with what I have. So 5.3 times 10 to the 13th, and my units are atoms. Okay, it's important that you write out all of your units, because as I go through this conversion factor, I'm going to need to cancel out units of what I have to get to units of what I want. Okay, so units that I have are atoms, but I want to get to moles. So how many moles? Well, I know that in any mole of a substance, there are 6.02 times 10 to the 23rd atoms in that substance. Okay, so Avogadro's number tells me that. So if I have 5.3 atoms and I want to know how many moles, well, my conversion factor would be that I know 6.2 times 10 to the 23rd atoms are in any one mole of any substance, okay? Whether it's a compound or just a single element. Here I have water, so I know that even in 1 mole of water, I'm still going to have this many atoms in that substance. Okay, so I can cancel out units now because atoms cancel, because one's on top, one's on the bottom, so I can cancel that, and it leaves me with my units of moles that I want. So what I need to do is this is over this, so you've kind of set up a fraction here. So 5.3 times 10 to the 23rd. Okay, if I'm going to plug that into a calculator, I'm going to put this part all in parentheses. Okay, and then I'm going to divide, so hit your division key and put this in parentheses here. Okay, Avogadro's number. So this divided by this is going to give you your answer of how many moles that you have, which is going to be 8.8 times 10 to the negative 11th. And that is Okay. All right, so we'll look at a couple others to kind of help with those conversions. All right, so now what is the mass of 15 moles of carbon dioxide? Okay, we know carbon dioxide is CO2. All right, so I'm going to start with what I have, which is 15 moles. Okay, so 15 moles is what I have, and I want to figure out what is the mass. Okay, so I know that any 1 mole is going to be the molar mass of the compound. Okay, so what I would need to do is find the molar mass of CO2. So again, just like we set it up before, we're going to have C, we're going to have O. Okay, now there's 2 O's. So carbon, we said if we look at the periodic table, is 12.011. Oxygen is 15.999. All right, we're going to multiply that by 2. So altogether, the mass is 44.009 grams. Okay, so this is the molar mass. Okay, that's the molar mass of that compound. So any mole is going to weigh the molar mass of the compound. So, and I kind of wrote this incorrect here, so I'm going to change that. So moles is going to go on bottom because that's what I want to cancel. Okay, so what I'm going to need to do up here in this space is put that molar mass there. Okay, so 44.009 grams. Okay, because I want to know mass. So this allows me to be able to cancel the units now. So moles, moles, cancel. I'm left with the units that I want, which is grams, which is a unit of mass. So because 15 and 44.009 are both on top of the conversion factor, it's multiplication. Okay. I have a 1 here. So if there is a number on bottom, you would have to divide this. So really you're doing 15 times 44.009 divided by 1. But because we know anything over 1 is itself, we're not really going to pay attention to the 1 here. So 15 times 44.009 is going to give me 660.135 grams. Okay, and you can round your answer if you would like to just like 2 decimals. All right, but there's my conversion factor from mass to moles. Okay, part C, how many moles are 150 grams of NH3? Okay, so I'm going to write what I have. So 150 grams of NH3. Okay, now we just said, like in our problem above, we went from moles to mass. All right, now we're kind of doing the backwards, mass to moles. So what I'm going to need to do is find the molar mass of NH3. Okay, so you know how to do that. NH, we're going to split it up. There's 3 H's, so I'm going to have to multiply that by 3. I'll find the mass of each substance and then I'll add them together. Okay, so I've already done that. So the molar mass of NH3 is 17.031 grams. Okay, so I've already got the mass, molar mass of NH3 made up. But again, just kind of extra examples of how to find that molar mass. So here I want to go I'm in grams, but I want to know how many moles. Okay, so with moles, what I want to find is going to go on top. What I want to cancel is going to go on bottom. Okay, so my grams are going to go on bottom. That's the molar mass, so 17.031 grams is 1 mole. Okay, so the molar mass of the compound is equal to 1 mole of the compound. So my grams would cancel, grams cancel. I'm left with moles, the unit that I want. So it's really 150, so everything on top multiplies, everything on bottom is dividing. So 150 times 1, which we know is 150. So really it's 150 divided by 17.031. Okay, which gives you 8.81 moles. Okay, so that's how many moles are in 150 grams of NH3. All right. Part D, how many atoms are in 0.23 moles of hydrofluoric acid? Okay. So here, I'm going to start with what we know. So 0.23 moles. Okay. And I want to get to atoms. All right. Now, here, it says hydrofluoric acid. I do not have to find the mass of that. I really don't even need to know what the compound is for hydrofluoric acid because my conversion is moles to atoms. Okay, so I know that any mole of a substance has 6.02 times 10 to the 23rd atoms in it. All right, I don't need to know the mass of it. Okay, so moles here. Okay, and I want to get to atoms. So I know that moles is going to go on the bottom. Atoms is going to go on top. Okay. So any 1 mole of a substance, so 1's on bottom, is equal to Avogadro's number in atoms times 10 to the 23rd. Okay. So 0.23. So moles cancel. I'm left with the units I want. So 0.23 times Avogadro's number divided by 1, which again is just itself. So when I plug that into a calculator, it's going to give me 1.38 times 10 to the 23rd. And again, that's atoms. All right, so there are your conversion factors for converting grams, moles, and atoms. Okay. Looking at part 5 now, or question 5. State the law of conservation of mass. Okay, well, the law of conservation of mass says that mass cannot be created or destroyed. Okay, it can't be created or destroyed, only changed. Okay, so we can kind of change around the forms that we have as far as states of matter, things like that, but with mass, it's not going to be created or destroyed. What we start with has got to be equal to what we end with. Okay, so question 6. What does the triangle mean if written above the arrow in a chemical equation? Well, remember that if we have a chemical equation, all right, we have our reactants, which is what we start with, products is what we end with. Okay, above this arrow here, if there's that triangle above the arrow, it means that we heated, okay, or added heat to the equation to be able to get these reactants to react and produce those products. Okay, so the arrow above means that you added heat, which is typical for many chemical equations, because if you add heat to some type of reaction, it's going to cause that reaction to occur or to speed up, and then leave you with those products. Okay, so the triangle above the arrow means that heat was added to get that reaction to start. Okay, this triangle you'll also see in some of your equations later, which does mean a change in, all right? So the delta, like when we have Q equals MCAT, all right, we had that change in temperature. Yes, it does mean that, but if we're specifically talking about if it's written above the arrow, it means that we added heat. Okay? Diatomic molecules. Okay, diatomic molecules are only going to exist in pairs. They do not, or they're elements that they're not going to exist by themselves. They're always going to be paired of another one of their cells. So, how I remember is Brinkelhoff, okay? Br, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Okay, the symbols all from the periodic table. All right, Brinkelhoff. All right, and we said they do not exist by themselves. So you're never going to see these elements in a chemical equation written like this. They're always going to have the subscript of 2 with them. All right, they only exist in pairs. They'll never exist by themselves. So that's what we mean by diatomic molecules. Di meaning 2, so they exist in pairs. All right. Number 8, which side of chemical reactions are products and reactants? Well, we kind of already covered that in question 6. We know that the reactants, okay, are on the left. Products, what is produced, is on the right of that chemical equation with the arrow in the middle, or the yield sign. All right. So there's your products and reactants. Okay, so now we're going to look at balancing equations. All right, so with balancing equations, we know that what's on the left has to equal what's on the right. Okay, so that satisfies the law of conservation of mass, which we talked about in question 5. So here with balancing equations, all right, the first two are really, first one's a little bit more time consuming. All right, to kind of save some time here, I'll give you those. So this one will have a coefficient of 2, this one will have 15, coefficient of 6, and 12. All right, so when we're balancing equations, we can only change the coefficients here, meaning the number in front, and those distribute to each element in the compound that it's in front of. Okay, we cannot change the subscripts. That does not satisfy the law of conservation of mass. If we're changing the subscripts here, then we're changing kind of the law of conservation of mass. All right, so we can only change the coefficients. All right. And really, if we're changing the subscripts, we're changing the entire compound that it is. All right. When I add a coefficient, I'm just saying, well, I have 6 moles of H2O here. All right, so I'm adding a whole nother compound anytime I change this coefficient. So I've got 6 compounds or 6 moles of H2O here. If I change that this subscript of 2 to like a 4, well, H4O is a completely different substance. It's not water anymore. All right. So that's why you can only change coefficients and not subscripts. All right. So when I'm looking to do my balancing, all right, I want to just look at question D here. I take an inventory. Okay. So what I mean is I'm going to write out each compound that's on both sides. So Fe, O, and H are the compounds, or are the elements that make up the compound. All right. And then I'm going to write out how many of each I have. Well, Fe is by itself, okay, in the front. This 3 is only attached to what's on the inside there of those parentheses. So Fe, I have 1. O, I have 3. H, I have 3. Okay, now Fe has a subscript of 2 over here. O has 3. Actually, there's 4 because there's 1 right here, 1 right there. So this one's 4. And H has 2. All right. So now from here, it's kind of a guess and check. So I'm going to try to match up one of these. So I know Fe has 1, but it has 2 over here. So if I add a coefficient of 2, I can make this Fe a 2 on this side. So now they kind of match up. But because I added a 2 here, and this is a whole compound, that 2 is going to have to distribute to everything that's inside now. So because I had 3 of each of these, it now multiplies by 2, so now I have 6 and 6 of each of oxygen and hydrogen. All right, now O and H are still not matched up on this side, so I'm going to have to go over here and change something. So if I put a 3, let's say 3, in front of that H2, well, now I've got 6, which matches, and then 3 distributes here, so now I've got 3 oxygens here, 3 oxygens there, all right, which gives me a total of 6. So now I've got 2, 2, 6, 6, 6, 6. All right, so now I'm balanced. I've satisfied the law of conservation of mass, and I've got that. Okay, so with the process, same thing. Focus on your subscripts. Okay, what they're attached to. So like this one here, this SO4 is not in parentheses. So this 4 only goes to the oxygen. S is by itself. All right. Now if I look here, this SO4 is in parentheses. So the subscript that is on the outside is attached to it. So 2 is attached to this, and then 2 is attached to that oxygen, which has 4. So total, I'm looking at 2 S's here, and total, I'm looking at 8 oxygens there. All right. So when I go through and I balance these equations, I should get a subscript of 4, 1, 1, and 2. All right. And then for C, you should get 4, 5, 4, and 6. Okay. So those should be the coefficients that you add for balancing equations. All right. Write the formula equation and balance the following formulas. Okay. So with nitrogen and oxygen react to form nitrogen dioxide. Okay. So if I say nitrogen and oxygen react, okay, that's my reactant. So I have nitrogen and oxygen. Okay. Now, we said that nitrogen and oxygen are both diatomic molecules, which means they can't exist by themselves. So they're going to have 2, react to form. So now they're forming or producing nitrogen, which is N dioxide. So O2. We know di means 2, oxide is oxygen, so NO2. All right, so this is our formula. Now we have to balance it. Okay, so I'm going to go through all of my balancing steps. This one's a little bit more simple. All right, so NO, and then I have N and O. So I'm not balanced because I have 2 of these on each side and only 1 here. So I'm going to add a 2, all right, which gives me 2 N's, but it also changes how many oxygens I have, so 4. All right, so now I've got to go back to this side, add a coefficient. So 2, which now gives me 4. So now 2, 2, 4, 4. I'm matched up. So I could put a coefficient of 1 here if I wanted to. I don't have to. It's not really necessary. I have a coefficient of 2 there and a coefficient of 2 in front of the NO2. All right. All right, sodium chloride reacts with magnesium to form magnesium chloride and sodium. So here, sodium Na, chlorine is Cl. All right, Na on the periodic table, we know has a charge of +1 because it's in group 1. We know Cl, it's needing 1 more to achieve that octet rule. All right, so NaCl, their charges are going to cancel. So this is a -1 charge. This is a +1 charge. They cancel out. So NaCl. Okay, with magnesium. So sodium chloride reacts with magnesium. Okay, so reacts with magnesium is Mg. Magnesium is not a diatomic molecule, so it can't exist by itself. So Mg to form. So produces magnesium chloride. So Mg. And then we know chloride is Cl. Now, magnesium, if I'm looking here, has a charge of +2, and we said chlorine has a charge of -1. All right, so with chloride, I'm going to have 2 chlorides to be able to react or to be able to balance the charge of the +2 magnesium. So what that means is this Cl has got to have a 2 in order to balance those charges. Okay, and then it says and sodium. All right, so plus sodium, which is Na. All right, sodium is not a diatomic molecule, so it can't exist by itself. All right, so that's how we get this equation here. All right, now what I'm going to have to do is go ahead and balance this equation. All right, so I've got NaCl and magnesium. NaCl, magnesium. Okay, so Na, I've got 1. Na, I've got 1. Cl, I've got 1. Magnesium, I've got 1. Then magnesium here, I've got 1. And Cl, I've got 2. So I'm not balanced. So what I'm going to do is add a 2 here. All right, which is going to give me 2 NAs now and 2 CLs. All right, now I'm going to have to come over here, put a 2, which is going to balance out. 2. So now I've got 2, 2, 2, 2, 1, 1. All right, so now we're balanced. So all of these coefficients in front, again, you can leave them blank, or you could say that they have a coefficient of 1. All right. So again, why do we balance chemical equations? Okay, to fulfill the law of conservation of mass. All right. So we're balancing those equations to fulfill the law of conservation of mass, which says that mass can't be created or destroyed. What I start with, okay, so what I started with on the left-hand side is going to equal what I have on the right-hand side. Okay, that mass cannot disappear. It can just change, and it has to be equal on both sides. Okay, so now we're looking at stoichiometry and water in solutions. So our first question here on number 12, calculate the percent composition of the following. With percent composition, okay, I'm using molar mass. So your questions from pretty much 1 through 4 on this review, calculating molar mass, that's a big part of it. You just have to take kind of an extra step. So we know with molar mass, C and F are my two atoms. I know that there's 4 fluorine, so I'm going to have to multiply by the mass of fluorine. So with carbon, I'm 12.011 as my mass of carbon. Fluorine has a mass of 18.998. Okay, which is going to equal 75.95. 75.95. Say 3. Okay, so add those all together is going to give me a total molar mass of 87.96. All right. So my molar mass is equal to this. So with percent composition, you're trying to find how much does each part weigh in relationship to the whole mass of the compound. So to find percent composition for each part, so I'm going to look at carbon. All right, so I'm going to take carbon. The mass of carbon's part is 12.011 grams over the whole compound, so 87.96. All right, so we know I'm going to divide part over whole, and then I'm going to multiply that number after I'm done by 100 to just convert it into a percentage. Or if you want to just do divide by this, move the decimal 2 places, that's fine as well. All right, by multiplying by 100, it moves the decimal kind of for you. All right, so here you have 13.65, and we said that's a percent. So with carbon makes up 13.65% of the whole mass of the compound. Okay, now with fluorine's going to have a higher percentage, 1, because each compound's heavier, and then 2, because there's 4 elements or 4 atoms of fluorine. Okay, so I'm going to again go back, take the part, which was 75.953, divided by 87.96. All right, so that's the part that fluorine has. There's the whole mass of the compound. When I multiply that by 100, it's going to give me a percent composition of 86.35%. Okay, so fluorine's percent composition makes up 86.35% of that composition. Okay, so again here, for part B, I've got Cu, Cl. All right, there's 2 Cl, so I'm gonna have to multiply that by 2. So you just find the total molar mass. All right, so here is 63.546. That's just straight from the periodic table. All right, the mass of copper. Chlorine is 35. What was it? 35.453. Multiply that by 2, which gives me 70.90 or 70.91. All right. So now add those two together. So I'm going to add those two numbers to get my total molar mass, which is 134.4514. Okay. So now I'm just going to take the part over the whole. So copper, 63.546 divided by 134.4514, the molar mass. Times 100 to make it a percent, which gives me 47.26%. Okay, so there's copper. Then I come back to chlorine, which is 70.91. The part divided by the whole times 100 to make it a percent is going to give me 52.74%. Okay, so with percent composition, we're just doing the part divided by the whole. Okay, part divided by whole. All right. 13. Okay, what is the percent composition of carbon in C2H4? So here with our problem, we're going to have to find the total molar mass, but it just tells us to find the percent comp of carbon. We don't have to find the percent composition of H or the other part here. Okay, so with carbon, all right, I have 2 of them. So carbon, there's 2 of them. It weighs 12.011 for 1 carbon. So when I multiply that by 2, it gives me 24.022. Okay, and then the mass, the total mass of hydrogen, I've already calculated, so to save some time, the total mass of hydrogen is going to be 4.032. Okay, again, that's the total mass after I multiplied one mole by 4. Okay, so the total molar mass of that compound is 28.056. All right, now I just want to know the percent composition of carbon, so I'm going to take that, divide by molar mass, 24.022, multiply by 100 to get me a percentage. Okay, so when I calculate the molar mass of carbon, or the total molar mass of the compound, and the mass that carbon is, multiply that by 100, it gives me 85.6% composition. Okay, I don't have to find the percent comp of hydrogen here because it just tells me to find carbon. All right. So now, what is the difference between empirical and molecular formulas? Well, with empirical formula, it's the most simplified version. Most simplified version, okay, of a formula. Molecular is one that can be simplified. Okay, so that makes a little bit more sense when we look at question 15. So with question 15, if I look at part A here, CH4, that formula or compound does not have anything that I can simplify, meaning the subscripts don't have a common multiple or anything. So because I can't simplify it, we're going to say it's the empirical formula, okay, or EF to shorten it. B, C has a subscript of 4, H or hydrogen has a subscript of 8. Okay, those have common multiples. 4 is the common multiple there. So I can divide each subscript by 4, okay, which would give me C would have 1, which I don't have to write a subscript for 1. 8 divided by 4 is 2, so now H is 2. Okay, so this would be the most simplified version of it. Okay, because it wasn't simplified at the beginning, we say that's the molecular formula because it could be simplified more. All right. C, 2, 4, and 1. I can't really simplify that anymore because oxygen is by itself. All right. So I could say 2 and 4 have common multiples, but because oxygen's there, this is the most simplified version. So it's an empirical formula. Okay. D, 2 and 6 are common multiples. Okay, so 2 is my common multiple here. All right, so 2 is 1, which I don't really have to write the 1, and then H would be 3. Okay, so what we started with was the molecular formula. Okay, CH2 is the most simplified version, so empirical formula. Okay.